Next, I'd like to invite Dedi, he is coming, from NexTenna to present. Give him a round of applause, please.
Hi, I'm Dedi, CEO and founder for NexTenna. Just a bit previously, I was with Google and then founded NexTenna. I'll talk about what we developed. It's a deep tech, and I'll do it briefly. NexTenna developed a new type of an antenna that allows us to build steerable antennas and multi-beam, both for ground and space. So, in short, we have two main components for the technology. The one on the right is the antenna itself, which contains a variable dielectric material that we developed, which is the base phase shifter, embedded into the antenna. And the second one is the controller itself. Now, the two most important features is that we reduced the cost of steerable phased array antennas by 2 orders of magnitudes. That's about $100 cost of manufacturing, and the controller is less than 15. So the total antenna is about $115 BOM, and that's what allows us to build terminals for space. So just to kind of understand on the, just behind me, this is an example of a terminal that operates with any satellite, whether GEO or LEO. The system is agnostic. The antenna contains the steerable electronic antenna. Controller has all the sensors to know where it's in the environment and adapts the phase distribution on the antenna to lock on the beam. And then, together with our radios, it can lock on any antenna. KU, KA, LEO, GEO, OneWeb, Starlink, any one of those components. What we do in space is very simple. We took that same technology and basically migrated that into space. The base wafer that we integrate into the antenna can operate under radiation, operates under very deep temperature range, and we can build multi-beam on board the satellite itself. We have over 26 granted patents. This is an example of our first product, NexTenna MP. It's a generic open source steerable terminal that can operate in KU on any GEO or LEO system, so it's a multi-orbit terminal. Operates on the ground, and we have an equivalent for space. 4 major advantages. Very low power. That means we consume 20 watts versus 350 on the same size terminal, and that's based on the phase shifter itself. It's a field effect phase shifter. Consumes barely 0 power. All the power is the buck itself and the controller. The controller is AI-based. The VDP is a variable dielectric technology built on the molecular level of the material. And we can scale it up from a small size, 4x4, to a baseball field. So you can communicate with anything as far as Mars. Those are the other co-founders, Rafael Barak, VP Business Development, Ilan, that's here, our CFO in operations. That's the team. We are focused on 3 different markets: consumer, broadband, transportation, and defense and space. Just kind of, the market today, I don't know if you're familiar, is about projected to be $196 billion on the terminals on the ground, and tens of billions of dollars on space, just on the multi-beam steerable antennas on the satellite itself. And we're targeting that market on both ends with very low power, very low cost. We're actually now seeking around the $15 million. That's our second round. We raised about 7.5 to date, and we're seeking 15 to scale production, scale the R&D team, and market penetration. We have a factory in Taiwan that builds this type of antenna every 15 minutes. That's including everything. And we need to scale it up for a mega factory, and that's part of the investment. We got traction from JSAT in Japan, part of the fact that everybody wants to have their own satellite. So JSAT decided to have their own system, not to work with Starlink or OneWeb, and they need a full system for connectivity for baseline infrastructure in Japan over a geosatellite. So we provide them the terminal. Just as an example of what we did in space, we got a grant from the IAA and took the same technology that we did on the ground, converted it to a space-grade antenna. And that's an example of our POC in space versus cesium that's taking their ground to space. So that's where we are. This is an example of a terminal on the ground, Kaimeta in the States. This is our technology, same G over T, same ERP, meaning the data rates are the same for the same price. 20 watts versus 350. This costs $20,000. That's about $400. That's basically it. Thank you.
Okay, we'll open the floor for questions from our esteemed panel judges.
I have a few questions. First of all, is it a wideband antenna or you need a different kind of antenna for every frequency?
No, it's very wideband. The phase shifter itself is based on a true time delay, so it's about 50% bandwidth. But every antenna, which you see the patches, those. So you have KU versus KA. So
it's different.
Yeah, you'll have KU and KA. So you have different tiles for a combination KU, KA. You'll have 2 tiles for KU, 2 tiles for KA, for example.
Another question, is it just for the space industry or you can use it also for the car industry?
You can use it anywhere, but we focused on the first low-hanging fruit on the global connectivity market, which is OneWeb and alike and the global geosatellites, but it's irrelevant. You can put it on a car, you can put it as a radar. It's really a deep tech. It took about, it looks short, it took about 18 months just to set up the production line. So this is kind of the...
What I understand is a multi-use sort of antenna.
Yeah.
But then isn't it more expensive by design if it's not curated towards a specific application?
No, so I'll explain. The key innovation is the actual phase shifters, the VDP, the variable dielectric phase shifter. That component can be integrated in any type of an antenna. The production factory we have produces KU, KA, or E-band at the same process. So it's not like a fab for KA like in semiconductor. It's the fab for all. And what we did, we migrated the complexity to the PCB layer. So we have a different PCB for a different frequency. So we're changing the dimensions of the printed patches. But the wafer itself is the same.
Same.
Okay.
Is the concept, I guess I'd say, scalable to optical comm, or is it strictly RF?
It can go to optical, but we haven't tested that. Because again, the key inside, just imagine we basically rotate the molecule. So we rotate the molecule and we created a waveguide so you can actually create that in optics or 90 gigahertz or terahertz. It doesn't matter. We just focused on microwave frequencies for that simplicity, in a sense, for product. But it's applicable to higher frequencies.
More questions? Yes.
The patents are granted, so it's in public domain. You can read it.
One more question is, how fast it can move, or it doesn't, between different bands in real time? If you want to change from satellite to another satellite and you want to change band, is it possible?
No, so you will have two. If it's KU, KA, you'll have 2 tiles. So simultaneously, you'll work with track a KA satellite and a KU, 2 different tiles.
Oh,
If you want to redirect the beam, it's sub-milliseconds. It's very fast.
I got it.
But frequencies, it will be a different tile, different frequency bands. Yes, that means KA, which is 30 gigahertz, KU, which would
So you need different kind of antenna for different kind of bands, and
Yes.
In between you can change the antenna that you're working with really quick.
Yes, and within the band, you can switch any frequency. So for
Yes.
example, KU is 10.7 to 14.5. Any frequency within that frequency is available.
Thank you.
Okay. Thank you so much, Dedi.
Thank you.